Welcome to my new calculus channel. I am John Gabriel. In this YouTube video I will be discussing division, long division and polynomial division. But before I do that, I'd like to explain what division actually means, because most mathematics professors don't even understand what division means. And although they're able to use it and they can arrive at correct results most of the time, they really don't understand what it means fundamentally. Okay, so if we have P divided by D, this symbol here, by the way, is called an obelus. This symbol here, okay, an obelus. The horizontal line by itself is called a vinculum. So this is an obelus, and the horizontal line like that or like that is called a vinculum, just so that you know. Alright, now P divided by D is equal to Q plus remainder. What does that mean? First of all, for this, for anything to happen in the statement here, P must be greater than Q. Okay? If P is not greater than Q, nothing happens. If you write something like this, nothing's happening there. Okay? No division has taken place. The division here has already taken place. It's finished. Well, you might say, well, how's that possible? Because we're saying P divided by Q. No. You're not saying P divided by Q. You're saying 1 or the unit divided into Q equal parts. Okay? And then you're saying how many of those parts you're interested in. That's why this is called the numerator and this is called the denominator, because it tells you what the denominations are. The denominations are all equal parts of the unit. Yes? Okay. And P, which is a numerator, numerates or counts how many equal parts you're considering. So it's actually, not strictly speaking, it's actually not true at all to say that this means the same as the vinculum. Okay? It does not mean the same as the vinculum. Well, you might say, well, what about when P is greater than Q in this situation here? Well, just in this particular instance where P is greater than Q, you could theoretically do an obelus operation, and then whatever remainder is left, then you'd have the quotient, let's say K plus a remainder R over Q. Okay, and in this particular instance here, and in all other instances where there is a remainder, no more division takes place. That's why it's a remainder. And it tells you how many parts of Q are left. And no further action is taken. There is no such thing as perpetual division. Okay? So you cannot, for example, start off something like this and go 3 goes into 1, 0, and then goes into that 3, remainder 1, 3, 3. That's just nonsense. Okay, there's no such thing. This here is absolute rubbish, and this is what your teachers brainwash you with. It's completely incorrect and meaningless, and you shouldn't be learning arithmetic this way. Okay, so now that I've told you about that, let's just get rid of that. And this. And this. Okay. And now, so how does this actually work? Well, here I've drawn the lengths of some lines here. This line here I've designated to be the unit. This line here I've designated to be 2 units, 3 units, 6 units, and 7 units. And so what if I had to say, well, what is 6 divided by 3? What does that mean? Okay, what does that mean? Well, this is what it means. It means, how can I measure 6, the line 6 with 3. You see the 3 here? How can I measure it? So I can go 1 and 2. Okay. So yeah, see what's happening here? I actually used the divisor to measure 6, and it measures 6 exactly 2 times. Okay, exactly 2 times. Similarly, if I were going to measure 6 with 2, so let's do this, 6 divided by 2, I would take my 2 unit like that, and I would see how many times it goes into 6. 1, 2, 3. 3 times, okay? So it goes into 6 3 times. So the answer here would be 3. Alright, now how about if I had to say something like this? So let's move this down here. Okay, let's say 7 divided by 2. What does that mean? Okay, well that means we take once again the unit, the unit or 2. Let's take 2 because we'll be able to measure it faster. Copy, paste. Alright, so how many 2's do we have there? 1, 2, and 3. And you can see that we're not going to be able to fit another 2 in there. But this part here is exactly equal to the unit. So we know that over here we're going to have 3, but there is a remainder, right? And the remainder happens to be the unit. Okay? There you go. So here's the remainder, 1. So 2 measures 7 3 times with a remainder of 1. In other words, with a remainder of 1/2. 1 or 1/2, okay? Remainder 1 means the same thing as 3 1/2. So this is generally written as 3 1/2 or 3 1/2 or 7 halves, okay? And in this case, P is greater than Q. So a division a la obelus is possible because P is greater than Q. If P is not greater than Q, then no division is possible and the number happens to be a fraction. Okay, so this is really what division means. And when we do long division and polynomial division, we are actually measuring, the dividend. We're measuring the dividend, which is P, using the divisor. And we're getting a quotient plus a remainder. Okay? So in this case here the remainder is 0, and in this case here the remainder is also 0 because 3 measures 6 exactly, and so does 2. And that's really what division is all about. Okay, so now that we've covered that, let's close this window, and we don't care to save it, and see in how many different ways we can actually perform division. So if you look over here, I've said, what is 60 divided by 15? Obviously 60 is the dividend, yes? 60 is the dividend and 15 is the divisor. But I can split the divisor into as many partial divisors as I like. Here I split it up into 7 plus 8. I could have also split it up like this, 5 plus 5 plus 5 if I wanted. Alright? It doesn't really matter what linear combination I split it up into, and I could do the same with the dividend. I just split it up into 2 separate parts, and the quotient really is just 4, but I've also split it up to show you that the quotient can also be formed from partial quotients, and so that you can understand why this process works. So now what I'm going to do here is I'm going to use 10 plus 5 and 40 plus 20. 40 plus 20 is 60, and 10 plus 5 is 15, right? So I'm still doing this particular division here. So now I'm going to choose this partial divisor, which is 10, and say 10 goes into 40 4 times, right? Then I will multiply both partial divisors by 4, because when I write a value up here, it means the entire divisor, okay? And you may say, well, we've only used the partial divisor. That's okay, because when I multiply this by this partial divisor, well, I'll get 20, which you see over here, right? This 20, but and so I'm actually subtracting this 20 from the total value. So it doesn't matter. I'm not actually just dividing by 10. I'm dividing by the whole partial divisor, as long as I multiply this partial quotient by both or all the partial divisors. So 4 times 10 is 40, and 4 times 5 is 20, and then I subtract it from the partial dividends, which is 40 and 20, and I get 0. So that's one way of doing it, okay? It doesn't matter how you do it. You can also choose 5 to be the partial divisor. And you can say, okay, well, 5 goes into 40 8 times, right? So 8 times 10 is 80, 8 times 5 is 40. Do a subtraction here, that's minus 40 minus 20. And then I could have carried on using 5 as a partial divisor, or I could just switch to any other partial divisor I liked here. I could have actually used 13 plus 2 here, or I could have used 15 here, or I could have used any other linear combination of the partial divisor. So all I do now is I say, well, 10 divides minus 40 minus 4 times, and I multiply it out by both of these. Minus 4 times 10 is minus 40, and minus 4 times 5 is minus 20, and the answer is 0. And of course, the final result is still the same. 8 minus 4 is equal to 4, right? So it doesn't matter how you do it. And here's yet another way to do it, as I've shown you here. There are no restrictions on how you choose your partial dividends. So for example, in this step here, I decided I'm going to switch from these values to these values. As long as they add up to the total, which is 60, I'm okay. So minus 36 minus 24 is going to add up to 60 in this case, right? Well, it's actually minus 60 over here. But as long as this adds up to this, you're okay with using any partial dividends you like. So you can mix your partial divisors and your partial dividends, and you can even change them completely, as long as they're equal to the original thing that you've got left over, okay? So as you can see here, I start off with 5, and I say it goes into 48 times, and I multiply out, and I get this answer, and then I just choose a completely new set of partial divisors. 9 plus 6, which is 15, right? And then I say 9 goes into minus 36 minus 4 times, and so on, and I still get the same answer, which is 4. Of course, I could do it in a very very weird way, like I'm going to do it over here. I'm going to use very weird numbers like 4 plus 11, 44 plus 16, but it doesn't matter what linear combination you use. So I choose 4 here as my partial divisor. It goes into 44 11 times. Then I multiply 11 by both of these to get that. Then I subtract this line from this line to get minus 105. Then I decide, oops, I'm going to change that to minus 99 minus 6. And I'm also going to switch my divisors around. Incidentally, I didn't have to even use 11 plus 4 here. I could have used 13 plus 2 if I wanted to. But just to not make it too complicated, okay, let me get rid of that. I just stayed with the same partial divisors, but I could also have switched my partial divisors here. So now I say 11 goes into minus 99 minus 9 times, and I multiply it by both of the by both of the partial divisors. Minus 9 times 11 is minus 99, and minus 9 times 4 is minus 36. If I subtract this from this line here, I'll get 30, and then I'll just go ahead. I could have stopped, by the way, I could have stopped right here and gotten the answer. I could stop anywhere and get the answer. If I stopped right here, I'd have just 11, which is this value here, minus 105 divided by total 15. And as you can see, if you carry out the arithmetic, you're still going to get 4. Okay? But I decided to continue, and I came over here. And if I decided to quit here and not continue the rest of this process, I'd still get the correct answer, because I'd have 11 minus 9. Hang on a second. I'd have 11 minus 9, this one here, which is here, plus the remainder 30 over 15. And if you calculate this out, that's 11 minus 9 plus 2, which is 4 again. So I'll always get the right answer regardless of what I do in my partial division process. And so this here tells you two things. It tells you, one, you can vary the linear combination of the dividend, the value that's under the radical sign, or the division sign rather, or the divisor, this here, okay? You'll always end up getting the same quotient. In other words, the total of the partial quotients will always be the same. As you can see, it's always being 4 in this case. And I'll show you the general theory behind this in a while. And the next conclusion is that you can vary which partial divisor or partial dividend you use. Okay, so for example, here you didn't have to use 4, you could have used 11. Or you could have just chosen a completely different set. You could have said 3 plus 6 plus 6, you know, or any other linear combination of 15. Similarly, you could have chosen any linear combination of 60 here. Okay, you could have chosen 20, 15, and whatever the remainder is, 25, right? So you could have chosen that, or any other one that you fancied. So now, what I've done here is I've just given you some background, and now I'm going to show you some of the theory behind it. Okay, so now if we go to the theory behind it, what I'd like to do is first show you what happens if we divide A by C plus D. Yes? Okay, so if we divide A plus C by C plus D, we get A over C, right? And this will give us AD over C, right? Which will give us minus AD over C. And then again, we're going to get minus AD over C squared. And so we'll have minus AD over C minus AD squared over C squared. Subtracting here again, it's AD squared over C squared. And so you can see that there's going to be a general pattern here, AD squared over C squared. Okay, I'm sorry, over C cubed. Yeah, because if you divide C into this, you'll get this particular value here. And so you can see that this is a general pattern, and I can give you a closed form of this by just taking the last term and dividing it by C plus D. Okay, so you know, if I stopped, say for example here, where I said AD squared over C cubed, then the last one that I'd have would be AD cubed over C cubed times C plus D. Okay, and that would be the closed form. Closed form. That's exact, by the way. That would give you exactly A over C plus D. Without that last term there, you'd always have an approximation here. And that's why things like 0.333 dot 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 and 0.999 dot 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 are absolute rubbish, because they're based only on this approximation part here. Okay, the closed form is the entire series, which is finite and has this last term. So now you can see, although I use just A over C plus D, if I replace A by A plus B, then I'll end up getting this series, okay, and finally this one here, because this here is exactly the same as that, excepting I've replaced a by a plus b, okay? Oh, well, it's almost the same. I've actually gone one term further here, and of course this would change to d squared without this, and this would become a plus d cubed over c cubed c plus d. Okay, so then this here would be exactly the same as that. You can see the theory behind it. Now, this is a reason why you're able to divide polynomials such as x squared plus 2x plus 1 by, let's say, x plus 1, right? It doesn't matter which way you do it. And the theory that supports it is the partial divisor, partial dividend theory that I've just explained to you over here. And so what you would do here is you could choose either x or 1, whichever one you prefer. It doesn't matter. And say x goes into x squared x, that's x squared plus x, and then you have to subtract these from like terms, okay? In which case you'd have x plus 1 remainder, and then that goes into there once, and so you've actually done the polynomial division there, right? But you didn't have to do it this way. You could have done it any other way you liked. Let's do it the other way. Just get rid of this. Okay, so now you could have, for example, here said x squared plus 2x plus 1, x plus 1, and then use 1 instead of x. Okay, so 1 goes into there, x squared, yes. This wouldn't really help you very much, but I'm just going to show you that you can do it. And then you'd have x squared plus x cubed, right? So subtracting these, you'd have minus x cubed. Now you could just switch back to this one. It doesn't really matter when you do it, but it doesn't really help you if you've got x's, because what you want to do is go from higher power to lower power. And so you could say that goes into there, minus x cubed, like that, and then you'd get minus x squared, and then you get minus x cubed minus x squared, and you'd be back to where you started. And you could either choose x or 1 again, so it doesn't really matter how you do it. And you could have also reversed the sense of this. You could have, instead of said 1 being divided into x squared, you could have said 1 divided into 1. So let's just look at that way. Okay, let's do it that way now. Get rid of this. Alright, so now, come on. Alright, never mind. Okay, so 1 goes into 1 once, and then we could have said that's x plus 1, and we must subtract these from like terms, okay? So we'll have x squared, because there's nothing to subtract from there. X from there is plus x, and there's no 1 left because 1 minus 1 is 0, right? And then over here we could have just switched over to the x and said, okay, well, let's say x goes into x squared x, right? And so it doesn't really matter which way you do it, you will always get the right answer. You could have also said 1 goes into x squared, but then you would have had the similar situation we saw earlier, which you don't really want. It will still eventually get you to the right answer, but it's like going round and round in circles, and you don't want to do that. Okay, so I've actually showed you a lot of things here that you've never seen in your life before. If you're a mathematics professor, you should be paying a lot of attention to this, because I know that you've never seen this in your life before. And I know that this is new to you. And you should strive to teach your students why they're able to do things in mathematics. And that goes for all you teachers out there too. Most of you are a bunch of morons. I'm sorry to say that. And it's just quite sorrowful that you're actually teaching mathematics, because you're not qualified and you're not competent to teach mathematics. That goes for most of you. Okay, so now this here is really the theory behind division and what it means, and we've seen quite a few examples. I'll do one last example here to show you. I could have done this here, right? I could have said 13 plus 2, again the 60 divided by 15, 1. And then I could have just said 13 goes into 26, 2 times, yes. So I could have said, well, 2 times that is 26, 2 times 2 is 4. Subtract them, I'm left with 30, right? Okay. So I could either carry on this way by saying, okay, well, that's 15. So I'll just say 15 goes into 30 plus 2 and I'm finished, right? So that's one way of doing it. So I could just say it's the same as 2 plus 30 over 15, right? 30 is the remainder, so it's 2 plus 30 over 15, which gives me 4, which is the correct answer. Or I could have carried on in any way I decided to carry on. Let's say I decided to choose 2 now instead of 13 as my partial divisor. So then I would have said 2 goes into 30 15 times, right? Okay. So then what is 15 times 13? Well, let's quickly do some long division here. So that would be 195 if I've done my math correctly, yes? Okay. So that would be 195 plus 30, yes? And if I subtract these, I get minus 195, like that, right? Okay. So now, I could actually break this up, let's say into minus 150 and minus 45. Do I really want to do that? I would rather break it up into, I can do that, but it's not going to get me to a result faster. So I think I'd rather make it, let's see there, 130 and, well, in fact, I'm going to change, I'm even going to change my partial divisor here just to something more reasonable. I'm going to change it to 10 and 5. Okay, so I'm going to break my dividend up here into 190 minus 5, like that, okay? And then I'm going to say 10 goes into minus 119 minus 19 times, right? Like that. And then that will give me minus 190, and 19 times 5 will give me what? Will give me minus 95, right? Minus 95, okay? And if I subtract these, I'm going to get 90, right? And how many times does 15 go into 90? Well, that shouldn't be too hard. Can we do that? 15 goes into 90. Well, we could even change our divisor here into 30 minus 15. And then say 30 goes into 90. How many times? 3, right? So it would be plus. And I'm doing all this randomly, as you can see. I'm not even thinking of any particular pattern. This obviously is not the most effective way. I'm just showing you that it works. So 3 times 30 is 90, and 3 times minus 15 is minus 45, like that, yes? And so I'm left with 45, and I know, for example, that 15 goes into 45 exactly 3 times, right? So plus 3. And now if I've done all my arithmetic correctly, this whole partial quotient should add up to 4, does it? Well, let's see. 2 plus 15 is 17, minus 19 is minus 2, plus 3 is 1, plus 3 is 4. So you see, I mean, I just did whatever I fancied there because I know the rules as I've explained them to you. So I will get the correct answer no matter how I do it. Obviously this isn't the most effective way, but I just decided to show it to you because many of you will have to learn long division with polynomials, and you probably don't understand how you can divide things like that by things like this, right? And so now you know the reasons why, because this here happens to be a partial, a dividend expressed as partial dividends, and a divisor expressed as partial divisors, and the quotient, which will also be expressed as terms which are in effect partial quotients. And of course the sum of those partial quotients will give us the quotient. Okay, now I'm really out of breath. This has been a presentation on long division and what it's all about, and I trust you have enjoyed it, and I hope you'll join me again soon. This is the New Calculus channel, and I'm John Gabriel.